Thanks, Mairead, and thanks for the invitation to present today on the NSAI's thermal modelling registration scheme and thermal modelling in general. This is kind of a brief overview of what I'd hope to cover. Again, there's going to be a lot of repetition here in this presentation on our previous speakers, but it's just to try to best explain thermal modeling, get you familiar with Psi values, what they are, and how they differ to the Y value, which is the single integer that is entered into DEEP to account for all of these effects. So we'll go through what a Psi value or Chi value is, how they feed into the Y value calc. We've spoken at length about ACDs. What's the benefit? We'll take a look at an example Y value calculation on the Appendix E house, I call it. It's the house that is given as the compliant example in the back of Technical Guidance Document Part L. We look at the other aspect of Appendix D2 on the overarching requirement to make sure that your details in the first are robust for, again, this has been mentioned earlier. And we'll take a brief look at Agrément certs for model methods of constructions and published Psi value tables within, or that are contained within them. So a thermal bridge to reiterate and go over what we've already discussed. So a Psi value is the measure of the additional heat loss associated with a junction, additional over and above that of the adjacent planar element. Like, so if you've got a wall U value of 0.18 and you've got, for argument's sake, a Psi value of a jam of 0.18, well, that's equivalent to having an extra 1 square meter of wall beside at that jam. So again, we've touched on the risks of getting these details wrong. Gives rise to large thermal bridges. This introduces internal cold spots on the internal envelope of the building, which give rise to propagation of condensation occurring, which in turn propagates mold growth, gives rise to an unhealthy living environment, respiratory problems, asthma, COPD, and various other undesirable toxins in the air. So just to go on to have a quick look at the publications and the rules that we use to carry out 2D and 3D assessments of thermal bridges. IP 106, BRE IP 106 gives us rules on how we calculate linear thermal transmittance at junctions. It also gives us some guidance on FRSI values, which again, we've gone through earlier on. Table 1 in IP 106 gives an internal FRSI, critical FRSI value of 0.75 for internal surfaces. So this is the value we use in dwellings typically to ensure that we are being robust in our detailing and we're not going to fall foul of any cold spots or internal surface condensation occurring for a normal dwelling with normal occupancy. Again, I think Andy might have touched on it earlier. If we're in a laundry or a swimming pool environment with higher humidity levels, the parameters set on the FRSI value are more onerous, set up at 0.9, which means an internal surface temperature of effectively 18 degrees or more. We carry out 2D and 3D thermal modeling of junctions to ISEN ISO 10211, and any software package that is validated against that standard fits the requirements for a package or computer modeling package that will correctly assess Psi values. We follow the conventions, as I said earlier on, that are derived from BRE 497. This is a publication developed by Tim Ward. I think it was just Tim Ward, was it? Graham Sanders from the BRE in Scotland, who I already alluded to, did all the background work for accredited construction details. It gives rules and conventions for assessing thermal bridge junctions. So if we take a look at a simple junction, just to get a sense of what the Psi value is, and excuse me if this is a repeat of what was done earlier, but I think it's important to just have a look again. It's Dara, I think, presented on something similar. We take a simple corner junction on plan. We calculate the U value through the planar elements. We then model this in our finite element analysis software, calculate the total heat loss out through the entire model, and then we subtract from that heat loss the U value of the green area, the U value of the, we'll say, red area, and whatever is the residual heat flow is the Psi value associated with 1 linear meter of that junction. Again, we go back to the Appendix E house. So when we know the Psi values for all of the bridge junctions in the house, we're able to sum them up to get a total amount of heat energy associated with all of those thermal bridges. We then reverse engineer it. We divide it by the envelope area to establish the Y value, which goes into deep. So, you know, deep is a simple tool in terms of we're just looking at the heat transmission out to the envelope of the house. And then we're looking at what space heating requirements is required to keep the house at a constant temperature. So the heat transmission takes into consideration the heat loss due to the planar elements, heat loss due to thermal bridging, and it also takes into account heat loss to designed and undesigned ventilation losses. But we're just looking at fabric heat loss here for the purposes of today. Okay, so this is a little study that we did back in 2015, and the technical guidance document part L that was in place at the time applies to this study. So it's obviously the 2019 values have improved. Okay, so we'll spend a little time here on this. This looks like a very complicated looking sheet, but what it is it's taking all of the wall, roof, floor for the Appendix E house. It's establishing the areas of all of them. It's applying the U values associated with the example in the old part L, and it's working out here the sum of all of the watt Kelvin heat flow out through all of the plane elements of the house, okay? So that's the heat transmission associated with the envelope of the house, not factoring in heat losses due to thermal bridging. So as an exercise, we looked at Y values for a range of values. So we have the spoken about 0.15 Y value, and we've given a 0.08, 0.06, and 0.03 to quantify the uplift in loss of heat. So with the 0.15, there was 36 watt kelvins extra associated with heat loss due to thermal bridging. Whereas at the 0.03, there was only 7. And if you look at the next line, which is the summation of the heat loss due to thermal bridging versus the heat loss due, with combined, fabric and thermal bridging, we have 102 watt Kelvin being lost for the default 0.15, and that drops down to 73 if we go down as low as 0.03 for the Y value. So there's, approximately speaking, a 25% reduction in heat transmission just by focusing in on robust detailing. So that has obviously a knock-on effect on the primary energy for the house, which drops from 68 down to 55. So in terms of a BER, what does that mean? There's 68 and there's 55. By just focusing on this thermal bridging aspects alone, we've managed to jump half an energy band in rating. So it's very worthwhile in this time of converging NZEB standards. It's hard to get gains, so it's definitely becoming more viable to perform assessments of thermal bridging. Like any gain is a big gain when we're down at NZEB standards. Again, this is in an effort just to get a sense, a further sense on the Y value. Again, we've calculated all the watts Kelvin going out through all the plane elements, it being 66 there. And if we divide that by the envelope area, we can arrive at a sort of an average area weighted U value for all the plane elements. And that's been 0.27. So your windows would be like up at 1.2 or, and it's compensated by the lower U values of the walls, floors, and the roofs to arrive at an average U value of 0.27. And Dara presented this in her presentation. If we consider that the average U value, not factoring in thermal bridging, has been 0.27, when we include for a 0.15, 0.13, the effects of the average U value jump from being 0.42, including thermal bridging, or could be down as low as 0.13. Again, this is another representation of the 25% uplift in building value, but it's just another way of coming at it, coming at the Y value and getting a better appreciation and understanding as to, it's thought that, oh, we'll just go with a default. But if you could just demonstrate, for argument's sake, that you could achieve ACDs at every junction at a starting point, you're down at 0.35 as being your area weighted average U value, including thermal bridging, Again, it's been said on numerous occasions, if we can just take the accredited construction details, demonstrate equivalence to them, which is a simple process of comparing your detail with an ACD, establishing that minimum thresholds as described in the ACDs have been achieved, say resistance levels of insulation at window jambs, sills, heads, at pinch points where we have throating at, say, an external wall eaves junction. Not very difficult to do, doesn't necessitate thermal modeling at all, Andrew. And we can go to this advantageous value, the Y value of 0.08. I think this has also been, it seems like my whole presentation has been nicked from me. Validity of the Psi values, the guys already spoke about the fact that in the published tables D1 to D6 in Appendix D of TGDL, there are target elemental U values there that you must achieve in order for the Psi values to be valid. And so the footnotes to those tables explain the allowable deviations in them. And I think Simon has already explained that it's like an aggregated deviation of plus or minus 20% is acceptable. So I suppose if, I don't know, is it the BR's responsibility to ensure that that's complied with, or designer? The designer, okay. So there's a bit of scope there, if you have deviations and, you're not beautifully falling under the U values there defined in column 1, 2, and 3 of those tables. There's a bit of scope there for field of application. So, and if one is just going with the backstop 0.15 value, and it's probably an easier, less headache-filled route for some, there's still an obligation under Section D2 of Appendix D to TGDL to perform an assessment to ensure that you're not falling foul of any risk of internal surface condensation. And as I said earlier on, if we're demonstrating equivalence to ACDs, well, we're operating in a safe space, and we'll easily fulfill this requirement. Just before I go on to some of the Agrément certs and modern methods constructions and Psi values, like one of the most important things, I keep reiterating this when I'm performing audits on registered thermal modelers, is there has to be a detail to accompany a Psi value. If there isn't a detail, nobody can build it. So for anybody to give me a Psi value without there being a fully detailed junction explaining how it is that building junction goes together, wasting our time, okay? So first and foremost, that is what I look for when I'm performing an annual audit of a thermal modeler. Show me the detail is the first question I ask. And if they can't show me a detail, I say, well, then that's it. That's a non-conformance and a fail. You have to be able to relay what's the Psi values and what it's based upon to the guys on site. So there needs to be proper details. And way too often, as Andrew has alluded to, that's a panic situation. The job's even on site. Blockwork is going up, and we're still trying to bottom out in this thing. It has to form part and parcel of the earlier design stages, because there's going to be a sort of design process with your thermal modeler. There's going to be an over and back. There's going to be, look, if we put a bit of insulation here, if we up the size of that insulation there, we're only, in fact, putting extra 20 mil of insulation, say, around the perimeter of the wall, but we're incorporating maybe a thermal block, a layer or two of thermal blocks there, but we're actually improving this junction fourfold. And it's not at a fourfold uplift in cost, like, you know? So it's an over and back process to get things right. See a lot of these problems now in podium slabs, you know, where you've got big, meaty, 650 deep reinforced concrete podium slabs, which transfer a car parking grid to a more suitable to apartment grid, you know, and massive thermal bridges there. So how do we get around those? We need to approach that at early design stage. Maybe the right solution is to go with insulation on top of that podium slab and a screed zone. You know, but those things need to be done early doors. And I do believe that as part of the initial submissions, that more and more developers out there are being asked to provide a suite of typical details that they build to demonstrate that they have thought about thermal bridging, they have thought about this. And as I said earlier, it's not, we're going to be modeling from here to eternity. It's 20 details. Get a pack of 20 details, robust details, how those pieces of Lego fit the final jigsaw puzzle is incidental, you know, but that's probably a safe way to go, I think. So we've, in NSAI, we are seeing a good amount of activity on the modern methods of construction, with the development of, you know, BIM being used to great effect, really, to assist with the development of these modern methods of construction in terms of either light gauge steel systems or modular building systems, which comprise of mild steel carcasses with infill light gauge steel. But these guys are building the model in BIM and outputting from that model the rolling, cold rolling schedule for every single section in the building. And it's going together on a production line offsite, like gloves, fitting, everything being precisely manufactured, like with a very low tolerance. And it had huge benefits in terms of construction times on site, where, you know, 6 or 7 modules measuring 12 meters by 6 meters by 4 meters wide can be assembled in a day. So very rapid development on site. It's just another example of this. Is a modern method construction roof using light gauge steel encapsulated in grey EPS, and then the core insulated foundation system giving very low U values. So as I said, we've got light gauge steel systems, which are panelized, a bit like timber frame without the shrinkage. We have a precast concrete system there with light gauge steel inner leaf as a new and innovative method of construction. And to that end, then, as I said earlier, look, on the tables, we will have gone down through a list of standard details which are applicable to these systems. We will have performed temperature factor checks, and we'll have produced Psi values for a range of U values. The U values in this particular one are listed down here as to the target U values of the flanking elements. So this is a timber frame system. Again, this is sort of a newer, more recent cert. We list the target U values for the flanking elements here and produce the certified Psi values. These are. And this would allow a potential customer of an Agrément certified product to maybe just perform a bespoke Y value calculation, just to establish, is this worth doing, and enter that into their provisional BER and garner an energy credit from it. As I say, we have a thermal modeling registration scheme that we operate. It's kind of, what is it, that's 20 guys. Some of them are industry representatives and won't offer that service, but there are enough there, I think, to provide that service. And, you know, once a sign certifier or architect or a developer has his preferred option, whether that be a cavity wall type solution, or whether that be a ICF solution, or whether that be a steel frame, you just need to go off and get, you know, the standard 20 details modeled, and that will be able to be applied across many different build-ups, house types, you know. But it's a good starting point, and with that, as part of a submission to local building control, it'll satisfy your requirements in terms of, are these junctions robust, fit for purpose, and not going to present an issue down the road. So a little faster than usual. That's for my presentation on thermal modeling.